So, in the last lecture we discussed about the response of a damped forced vibration single degree freedom system model, where this was the equation of the response x of t, which is the combination of the complementary function and the particular integral, where we have the transient response part and the steady state response part, because this is a function of force frequency, whereas this is a function of the natural frequency of the system. We know that omega d, the damped vibration frequency, is a function of the natural frequency of the system, which is a system characteristic. And of course, this depends on the initial conditions, whereas C and D does not depend on initial condition, where we know that C is P naught by K and D is minus P 0 by K. The same denominator. So, it does not depend on initial condition of x 0 and x naught 0. Therefore, this response will always exist in a given response equation, whereas this may depend on the initial conditions of x and x dot, and may vanish depending upon the availability of the boundary condition or the initial condition given to the response. So, we call this a steady state response and transient response. Now, let us pick up this equation. Maybe this was equation number 10 or 11, I do not know, let us say 10. So, let us substitute this value and see what happens to my equation x of t when the natural frequency is as the same value as that of the excitation frequency, because this is solved when omega not equal to omega n. Now, let omega n be same as that of the excitation frequency. We call this as resonance response. The objective of this derivation is to understand that if I introduce damping, even at resonance, the buildup will not infinite, it will decay. We have to see that, because we already saw in a damped, in an undamped forced vibration, the response was building up by pi value at every cycle, and it is becoming unbounded at the resonance frequency, whereas in this case we have the objective is to check whether is it still the same case in case of resonance response. That is the objective of this derivation. So, we know the complementary function will not change, which is going to be as same as E minus zeta omega n t of A cos omega d t plus B sin omega d t, which will not change, whereas the particular integral has got to be evaluated now, which will be P 0 sin omega t by, there is a P 0 by m here, because you divide the equation of motion entirely by m, d square plus C by d of C by m of d plus omega n square. That is the particular integral for this particular problem. Now, we know the rule, for example, if the excitation function is a sinusoidal or a trigonometric function, I must say d square is minus omega n square or omega square. So, substituting d square as minus omega square as per the rule, and also recollecting omega n as same as omega, that is the resonance part, we are looking at that is what we are looking at. Therefore, these two will go off, my P I will simply become P 0 by m sin omega t by C by m of d. So, we can also say P by m sin omega t by 2 zeta omega n of d, because we know C by m is 2 zeta omega n. Then we can say P0 by m, let us say d square of 2 zeta omega n d of sin omega t which becomes minus P0 by m, because omega d square is minus omega square, so I get minus P naught by 2 k, because omega n square is k by m, this omega n goes away, cos omega n t. That is my particular integral. So, my entire solution or the complete solution will become e minus zeta omega t of a cos omega dt plus b sin omega dt minus P naught by 2 k zeta cos omega. Here I write omega n or omega, does not make a difference, because I am looking at the function at omega equals omega n. So, it does not make any difference. So, let me call this equation number 11, which is the response time history for a damped forced vibration at resonance. Okay. Now, let us go back to the general expression. I will get back here again and try to derive the dynamic amplification factor. Let us see how do we do that. So, the general solution is given by, this is a specific solution where x of t is derived at omega equals omega n. The general solution is what we wrote earlier, I am writing the same equation back again, is given by x of t e to the power of minus zeta omega n t of a cos omega dt plus b sin omega dt plus P0 by k 1 minus omega by omega n the whole square that is the general solution. Now, let us talk only about the steady state response part of it. To make this equation in a combined or a closed form, we will express two ratios. Let beta be the ratio of the frequencies. The steady state response is given by, let us say x of t, I am looking only at the steady state part of it, P0 by k 1 minus beta square by 1 minus beta square square plus 2 zeta beta the whole square of sin omega t. We are writing this as a ratio as beta minus P naught by k 2 zeta beta by cos omega t. Okay. Let me call this equation number 12. Now, I can express this equation 12 graphically, because there are two components here, sine component and cosine component. Let us write it carefully. This is cos, using what is called as an Argand diagram. So, we can draw an Argand diagram and we can write this. He expresses graphically. There is an advantage of writing this. I will show you how. Let us say there are 4 quadrants of this diagram. This axis represents the imaginary part, this represents the real part. So, I have got 2 values, 1 and 2. I would say that they are offset from the vertical axis by an angle omega t, and I complete the parallelogram to get my resultant, which is R. So, let us say that this arm, when I swing away from the angle, I must get the sine component, which is positive. So, I must say that this value should be 1 minus beta square by root of 1 minus beta square plus 2 zeta beta the whole square. There is a multiple of p 0 by k is also there, this whole square of p 0 by k. Whereas, we all know that this angle is also going to be cos omega, this is also going to be omega t, because the angle between the values are 90. But as far as the cosine component is concerned, it is negative, okay, it is negative. Therefore, this value is going to be 2 zeta beta by the same denominator multiplied by p naught by k. I can now easily find the resultant of this by squaring and taking a root of the sum of squares. So, let us say what is the resultant of this, and let us say the resultant is making an angle of theta with this. Let us say this angle is theta. The resultant of this, the sum of squares of this, so if you sum of the squares of this p 0 by k, you get the numerator as root of 1 minus beta square plus 2 zeta beta the whole square, of course, the squares of this, divided by sum of the squares of this. So, it is 1 minus beta square the whole square plus 2 zeta beta the whole square, which will amount to p 0 by k 1 minus beta square plus 2 zeta beta minus of. Now, I can express x of t, which was the original equation 12, the steady state response part, making use of this expression now, which can be rho sin omega t minus phi minus theta, where rho is the result, which is given by this equation. This is equation number 13. So, R, which is also equal to rho, given by this equation, p naught by k minus of, or you can write it like this the other way, it is one and the same, it is p naught by k 1 by square root of 1 minus beta square plus 2 zeta beta whole square. Whatever way you want to write, you can. So, you can remember this easily. R. Now, from the expression there or from the Argand diagram there, I can also write tan theta. The theta is the angle between the resultant and the arm here, is this value by this value, which is 2 zeta beta by 1 minus beta square, the denominator will get cancelled. Now I can say x of t by rho, because okay, x rho is x static of, okay, rho is x static of, that is what it is, x static of some value. So, therefore, rho by x static will give me the dynamic magnification factor, which will be root of 1 minus beta square square plus 2 zeta beta whole square. Okay, that will go to the denominator. So, 1 by root of this value. Now, we know beta is omega by omega n, that is what beta is, and zeta is c by 2 m omega n. We can plot this equation for different values of beta and zeta. I call this as value of beta, and of course, this I will plot the dynamic amplification factor d at beta equals 0, let us say at beta equals 0, at beta equals 0, d will be 1. So, it starts from 1. And let us say beta at 1, 2, 3, 4, 5. Beta 1 means omega equals omega n, it is a resonating band. So, approximately at this band, let us say at this particular point, if zeta is not present, if damping does not exist, we have already seen that the response will become unbounded, will slowly shoot up, will go to infinity unbounded, then once the band is shifted, will slowly come down. This is for zeta equals 0, there is no damping. Now, for any other value of zeta, in D equation, you will see that the response will never be infinity, okay, there will be some finite value. Let us take zeta at 0.2, 20%, 0.2, the value is somewhere here. If you substitute, you will see, start from here, it goes here and comes down and merges with this. Let us say this is zeta 0.2. Similarly, data at 0.5, and so on. So, for different values of zeta, the dynamic amplification factor keeps on decreasing. It means the observation is d decreases with zeta increases. At zeta equals 0, d becomes infinity. However, this happens only for a narrow band, very narrow. D becomes bounded for all values of zeta except zeta equals 0. everywhere there is an upper limit of d. Now, the argument was what happens to x of t when zeta is not equal to 0 and omega equals omega n. That was the argument what you are looking at. At resonance what happens? So, at resonance when beta is equal to 1, for zeta not becoming 0, the dynamic amplification value is bounded. Let us see what is that upper limit of that value. So, let us take the equation of d back again and check what happens. So, d is 1 by root of, let us say 1 minus beta square of square plus 2 zeta beta the whole square. At v equals 1, d actually closely becomes 1 by 2 zeta. This is analytical, from the equation, and that is what happens here. Now, by experiments, people have conducted experiments and they have found that beta peak, that is response at beta equals 1 at peak, is found at 1 minus 2 zeta square. Substitute this value back in this equation, you will get d as 1 by 2 zeta root of 1 minus zeta square. For very small value of zeta, this equation will give you the same expression as analytical. Okay. This equation will give you the same answer as that of analytical for small values of zeta. So, they match. Therefore, x of t at resonance x of t at beta equals 1 is e to the power of minus zeta omega n t a cos omega dt plus b sin omega dt plus minus p 0 by k 1 by 2 zeta cos omega t or omega n t, does not matter, because I am saying beta is 1. This already we have derived, that was equation 11 or 10, I do not know, you can check that. This is my response. So, what does it mean is x of t, which is the response of a single degree freedom system, is a closed form solution for beta equals 1, provided zeta is not 0. You have a closed form solution. Okay. Now, let us say the system starts at rest, let x 0 and x dot 0 be 0. Let us see what happens to x of t. I call this equation, let us say 13a. Let us check 13a and see what is my x of t. Applying this condition, because if you apply this condition, a and b will go away. You can evaluate. So, just evaluate a and b and tell me what is the final answer for x of t applying this condition for this equation. So, I will write it down here. It is going to be p 0 by k 1 by 2 zeta e to the power of minus zeta omega n t cos omega dt plus zeta by root of 1 minus zeta square sin omega dt minus cos omega nt. 1 by 2 zeta cos omega nt is already there. Let us quickly look at the response ratio, call this equation 13b. 13b is nothing but the value of A substituted for A and B from the initial conditions. Now let us find the response ratio. Which is x of t by x static, because I have got P0 by k here, which is x static, which will give me R of t as 1 by 2 zeta of the whole value. Equation 14. Same value will come back again. Now in this equation, let us say for small value of zeta, that is damping ratio, you will see that omega will be practically equal to omega d, whereas omega d is omega 1 minus zeta square. So, for small values it is going to be equal. Therefore, my R of t for small values of zeta, so this will practically be neglected, it is a very small value. It will become 1 by 2 zeta, 1 by 2 zeta, because P0 by k goes here, that is my response ratio, e to the power of zeta omega nt. There is a decay, that is why it is minus exponential decay of cos omega nt, omega d and omega n will be almost equal, of cos omega nt, taking this minus cos omega nt. Is that okay? This term is there already. So, I can say 1 by 2 zeta e to the power of minus zeta omega nt minus 1 of cos omega nt. Equation 15. This is my response ratio. Now, interestingly, I want to capture the behavior of response ratio at zeta equals 0, undamped system, what happens to it, because we know that the moment you provide damping there is going to be a decay. So, in the previous case what we did was, we said damping is not there and we captured omega equals omega in the response and we said it is unbounded and it keep on increasing pi every cycle. That is the previous case. In this case, if we substitute zeta as 0, this equation cannot be valued because it goes to infinity, is it not? So, I have to apply Lee-Hospital's rule. I will apply this and try to modify this equation. So, for zeta equals 0, equation 15 cannot be evaluated. So, apply Lee-Hospital's rule and evaluate this. So, if you do that, R of t will now become 1 by 2, sorry, sin omega t minus omega t cos omega t. Equation 16. Now, I want to compare both the equations. Which equations I will compare? I will compare equation 16 or I will compare 15. Let us say I will compare two equations now to really check the response build up. Now, I want to compare the response build up. One equation I have is this, which is R of t is 1 by 2 zeta e minus zeta omega t minus 1 of cos omega t. The other equation I have is half of omega n t cos omega n t minus sin omega n t. So, the response build up for this we know look like this. And we already said by every cycle it is increasing by pi, whereas in this case it will increase and become steady. So, the upper bound is 1 by 2 zeta. So, this is the damped system at resonance. This is undamped system at resonance. So, one can write quick observations about this, comparing both these plots. The first observation one could write is, in both the cases the response build up is gradual. For zeta equals 0 undamped system, response shoots up to practically infinity at large number of cycles. This is very important. The shoot up of response to infinity is not instantaneous. It gradually picks up. What does it mean is, this gradually disintegrates or damages system. We can infer one more important point from this. Once the system is said to be damaged, omega n of the system, because both are at resonance, then the equation omega n or omega does not matter. Omega n, which is a function of root k by m, will change. Why? Because k decreases due to strength or stiffness, degradation. That is what we address as damage. Once stiffness or the strength degrades, omega either decreases, therefore, omega will no more be equal to the excitation frequency. The system will exit the so called resonance band. It will not stay in that band, it will come out of the resonance band. That is a very interesting characteristic of the system itself, which is used in the design of offshore structures. We can write one more observation, which I will remove this and write. At zeta not equal 0, that is for a damped system, even at resonance, assume that the resonance band is wide enough to further cause damage to the structure. So, even at resonance, the response is bounded at 1 by 2 zeta. It means even for a small value of zeta, the binding is highly controlled, because in denominator. That is why even 2% zeta will work. You can also quickly see this plot to understand the comparison between underdamped and overdamped systems. Let us plot a ratio. Instead of beta, I can also plot T by Tn, because both of them are 2 pi by T, omega by omega n. I can plot like this also. Let this be xt by x static. Starts from 1, we know that the response ratio is 1. If the system is critically damped, what is meant by critically damped? Critically damped means zeta equals 1, that is what critically damped is. If the system is underdamped, let us say zeta is 0.1. The system is overdamped, the response bulges out and becomes 0. You must notice some observations from this figure. 1. In all the 3 cases, critically damped, underdamped and overdamped, response is set to 0. It means analytically all the solutions will lead to recentering capability. In case of critically damped system, the response ratio is instantaneously brought to 0. So, the damage will be extensive. And system will fail without any warning. That is important, because the damage is instantaneous. In underdamped system, the decay is progressive, decay of the response, not the system. Decay is progressive, because looking at R of t is progressive, and it will enable some elastic behavior in the system. It enables some elastic behavior to the system. The moment I say it enables elastic behavior, stiffness of the system changes. The moment stiffness changes, omega n changes, and the whole argument of omega equals omega n at resonance is not valid. In case of overdamped, large amount of members will be affected. To understand this, you must convert this time history response to the frequency domain response and a spectrum. You will know the energy of the spectrum. So, you will obviously see this will have lot of energy. So, the damage caused to the large members will be higher. So, therefore, in general in structural engineering, people never prefer overdamped system. Critically damped is of course hypothetical. People generally prefer underdamped systems only because of the validity that even for a small value of zeta, even at resonance, the response will get bounded. So, there is no problem, and we generally go with 2 to 5% maximum in offshore structures. So, that is about the discussion on response behavior of underdamped and damped at resonance, response behavior of critically damped, under and over damped, not necessarily at resonance, but in general. This is the understanding what we physically gain, which will help us to design the system, because these equations and these understanding should be able to now emerge to design the system in a structural form. One may ask me a question, how this will help me in suggesting a new geometric form for an offshore structure. I can quote one simple example in a minute and show you how it can be done. Let us talk only about damping. There can be different sources. One can be material damping, one can be external source of damping, one can be an additional response control devices. As dampers. Suppose you understand that the hydrodynamic damping or the material damping or the structure's inherent damping is lesser. You can introduce an additional control device in a system so that you can bring down the instantaneous response in less number of cycles. So, recentering can be faster. The objective is not the response control, the objective is recentering can be faster. A classical example of this is multi-leg articulated towers. It is a classical example of this, where the buoyancy chamber is shifted in such a manner that the recentering is brought faster. So, buoyancy chambers introduce additional damping because of hydrodynamic effect, sloshing, etc. Okay? Because of variable submergence effect, this causes additional damping and that brings the objective. So, this is a design objective. Okay. So, all these inferences can be converted to an understanding of design. Similarly, in case of triceratop, with a new geometric form which is coming up for ultra deep waters, people introduce these are buoyant legs, this is the deck, and people introduce ball joints in between them. So, whatever response the buoyant legs will have, of course, the water level is somewhere here, the ball joints are above the water level, whatever response the buoyant legs will have, they will be absorbed by the joint, it will be transferred to the deck. If the deck has some aerodynamic response, it will be again absorbed by the joint, it will not come back to the legs. So, you are introducing an additional damping characteristic, fundamentally to bring the recentering capability more. So, the design is understood from dynamic behavior as a fundamental equation like this. Thank you.